Picking up where we left off, the question is, when that switch is closed, what will be the initial current through the 20 and the 10 ohm resistor? Now think about this for a second. You got a capacitor in there, but it's empty. The moment that switch closes, that capacitor acts like a wire. There's no charges here to repel any incoming charges. So whatever comes in just goes out the other side. So just ignore the capacitor. We can now see that the 20 ohm and the 10 ohm resistor are in parallel, and we have 9 volts on this side, 0 volts on that side. So we know what the voltage is across each one. So we have V equals IR. The voltage is 9 volts, and we know that the resistance is 20 ohms. The initial current through the 20 ohm resistor is 0.45 amps. And we can do the same thing with the other resistor, and it's 9 volts equals the current times 10 ohms. And we get 0.9 amps. Now we put the capacitor back in and ask ourselves what's going to happen in the end. The current flowing into that capacitor will eventually fill it all up. Nothing can get through. It's going to act like a break in the wire. If nothing can get through, how much current will be flowing through the 10 ohm resistor? Nothing. Using Ohm's law, if we have 0 current, I don't care what the resistance is, the voltage drop across that resistor is going to be 0. What does that mean for the voltage drop across the capacitor? It's going to have to be the voltage drop from here to here. Well, that's going to be 9 volts. So in the end, the current is 0 through that resistor. What about the current through the 20 ohm resistor? It's still got 9 volts across it. Nothing's changed here. It's still going to be the exact same math. And we'll have 0.45 amps through that one at the end. Now, what about finding Q on that capacitor? If the voltage drop across here is 0, that means the voltage drop across here has to be the rest, which is 9 volts. So we can say the capacitance is charge per volt. And we say the 0.05 farad capacitor is equal to Q over 9 volts. And we get 0.45 coulombs of charge on that capacitor. And I have to tell you, that's just some luck the way I set up the numbers. You think we're done? Nope. What's going to happen if we open up that switch? You might initially think that, well, the battery's disconnected, so nothing's going to happen. But that capacitor has charge in it. Where does it want to go? Those positives are going to want to start to flow around this way and go into the negatives. So we could ask ourselves once again, what's the current through each resistor? The circuit as shown now has the resistors in series. So we can say that the current will be the same through both of them. The total resistance is 30 ohms, and that voltage is 9 volts, giving us a current of 0.3 amps. Let's talk about the energy in a circuit like this. When the switch is closed, that capacitor is going to start picking up the charges. It'll eventually get all filled up. We know the current will stop flowing. So in the end, the question is, how much waste heat was produced by the resistor? This can seem really challenging at first because the current is going to continuously be changing, and how are we going to calculate the waste heat with all that changing stuff? But the key is you want to look at the capacitor. A graph will help us see it. The voltage and the charge build up on that capacitor. Eventually, we reach the final voltage and the capacitor is filled. And that's going to be the voltage from the battery. Using the formula for capacitance, we get Q over 3 volts equals 2 farads. And the final charge is going to be 6 coulombs. That gets put on the graph. So what does the area of this triangle represent? That's the voltage times the charge that got put on the capacitor, and the area would be Q times V, but it's a triangle, so it's 1/2. That's the potential energy stored in the capacitor. That's 9 joules. Now we can ask how much energy came out of the battery. Every charge that came out of the battery came out with a full 3 volts. What does that look like on the graph? Every charge that came out of the battery all came out with the full voltage. That is the area of this rectangle. What would that area of that rectangle be? 18 joules. And that would be the work done by the battery. Now, where did the rest of the energy go? We put out 18 joules. The capacitor stored 9 joules. Well, that must mean the resistor produced 9 joules of waste heat. That is going to be the rest of this triangle right here. So we can say the work done by the battery is equal to the potential energy stored in the capacitor plus the waste heat generated by the resistor. And there we have it. Resetting the problem, we're going to close the switch and watch the voltage increase on the capacitor. The voltage and the charge build up. Now, what was going to happen if, as we wait longer, this voltage eventually doubles on the capacitor? What happens to the potential energy stored in that capacitor? If you're a formula person, you're going to look at this formula and say, oh, the Q doubles and the voltage doubles, so the potential energy goes up fourfold. The same is true if you use this formula. If the voltage doubles, that's going to go up fourfold. The capacitance stays the same. But let's look at the graph. That's the energy at the halfway point. When we double the voltage, the energy is the area of the whole triangle. And you can break that up into geometric shapes and have 4 equal small triangles. So whether you look at the formulas or the graph, you get the same idea. Now in this example, we're going to look at voltage versus time. When we close the switch, which circuit element has the biggest voltage drop, the resistor or the capacitor? Well, since there's no charge on the capacitor, there's no electric field in here, there's no voltage drop. It's all occurring here. And that means whatever the voltage gain is on the battery, that's your voltage drop across here. The current's at a maximum, the voltage drop across here is at a maximum. So we say at time 0, the voltage across the resistor is at a maximum. The voltage across the capacitor is 0. And as time goes on, the voltage across the capacitor is going to start to increase because we're gaining charge on the capacitor, which reduces the current, and that's causing a smaller drop in voltage across the resistor. As time goes on, the voltage increases on the capacitor, but at a slower rate. And the voltage across the resistor, that's going to taper off to 0 because the current's going to taper off to 0. Can't have any voltage if you don't have any current through that resistor. Now, what do you think these voltages add up to? They add up to a constant amount, and that's the voltage of the battery. The resistor and the capacitor are in series, so of course these voltages add up to the voltage of the battery. Let's try another lab. First, we're going to charge up a small capacitor. You take your batteries and you connect the capacitor to the batteries and you charge it up. Then you disconnect that capacitor and you connect it to a second empty capacitor. The question is, when you close the switch, what will be the final voltage on each capacitor? Now that's something that you can measure in the lab. So imagine the charges on the first capacitor. When will they stop flowing to the second capacitor? A lot of kids think when the capacitors have the same amount of charge on each. But you got to consider that one capacitor is smaller than the other. There's just not as much room for it. How about the voltages? Remember that voltage is potential energy per charge. If this capacitor started with more potential energy per charge, those charges will flow to a lower potential energy. That raises this potential energy while this potential energy goes down. Eventually, the potential energies are equal. That's when it'll stop. So in the end, the top one will probably have more charge than the bottom one because it's got more capacitance and it's going to have the same voltage. Well, where do these charges come from? We can say that Q1 and Q2 came from the original charge on the first capacitor when it was charged by the battery. And that'll be found from the capacitance times the voltage on the battery. And we have 0.3 coulombs. So this charge will be distributed between these two capacitors. So we can say that Q1 plus Q2 equals the original charge. And we can replace Q1 and Q2 with the capacitance and the voltage for each one. Now, since V1 final and V2 final have to be the same, we can factor them out. And now solve for V final. And we get 2.14 volts for each capacitor, which makes sense because that number is lower than the 3 volts. It's the same voltage because these are just wires connecting these capacitors. The voltage here has to be the same everywhere on that side, and that has to be the same everywhere on this side. So the voltage drop obviously has to be the same. Now, this is all testable in the lab. You get yourself a capacitor and hook it up to a voltage, but you got to measure that voltage and write it down. Then you get the second capacitor and you build this, close the switch, and then you calculate the predicted values for your final voltage, and then you measure it and see how close you are. And that's a simple little lab. Now let's take a look at the energy. The initial potential energy, we'll say, is 1/2 CV squared. That's the initial potential energy, 0.45 joules on that capacitor. What do you think the final potential energy should be? And we'll have 1/2 CV squared for each one of these. We get 0.229 joules for the top capacitor. And we have 0.0916 joules for the bottom capacitor. Well, what do these energies add up to? Wait a second, 0.321 joules? What happened? We had an initial potential energy, and then we had 2 final potential energies. Where do you think the rest of it went? Had to be waste heat. It can't really be kinetic energy. We don't factor in kinetic energy with the electron moving in a circuit. There has to be waste heat to account for this difference. Even if we think there's no resistance, there's going to be some. It turns out there's a big difference in the slight internal resistance. It turns out there's a big difference in the internal resistance of our regular capacitors, which kind of look like a small can, versus the disc-shaped supercapacitors. The manufacturers state what's called the equivalent series resistance. For the smaller can-type capacitors, it may only be 1 milliohm, but for the supercapacitors, it could be 3 ohms. And so that'll significantly reduce the amount of current that you can draw from this capacitor.